Great, thank you so much. And yeah, I don't know, what an incredible week. I feel inspired and rejuvenized and just happy to do math with like amazing mathematicians and really good people, which maybe isn't always, I don't know, sorry, I shouldn't say that kind of thing out loud. It's true, it's true. Everybody is a good person at some time in their lives, so we'll just go there. And actually, just kind of piggybacking from what Ben had said earlier in the week, yes, I have a grant, and so I am funded by NSF, right? So I have to give props, sort of legally. And then also, they have a website where if you have questions, and I'm using it as also a venue to post my concerns, check out this QR code and send them your thoughts. I have done it multiple times already, and yes, you can use the same email and they will not restrict you to one comment, is what I found. And in particular, I feel a little bit nervous about saying this, but I just want to sort of highlight a little bit of the severity because on Tuesday now, Ted Cruz posted this press release. He is head of the Senate Committee on Commerce, Science, and Transportation. Somehow uncovered already public knowledge of NSF grants that support good things. And I'm on this list. So yeah, I don't know. What do you do with that? I'm not really sure. And I guess we're going to find out. But it makes me ask a lot of questions, for sure. And I know that I do mathematics, and I try to do mathematics with people. And I try to do mathematics with a wide variety of people. And apparently some people don't like that. So anyway, again, places to voice your concerns. One of them could be here. So, which I did. I made sure to at least send a message to them with the link to that document.
We love you and we love your mathematics.
Yeah, thank you. I'll make sure to cry later in the bathroom. Something you learn how to do very well at Berkeley. Okay, oh, sorry. I also try to do stand-up comedy on the side, so maybe, it's a joke, people, it's a joke. Okay, so moving on. Okay, let's do some mathematics, as people like to say. So this is a research team I've been working with for quite a while. It's been a lot of fun. We've gone through a few iterations, but here are all the collaborators that I've had the pleasure of working with in the last couple of years. Hopefully most you recognize, and we are an international collaboration. We got Jose Luis in Colombia working with us abroad. And this is a bit outdated. I think Jessica might have moved on to bigger and brighter things, but there you go. So we've been, oh, that's true. Oh my gosh, you're right. I'm sorry. Yeah. Has anybody embarrassed you yet with your, yeah. Okay, sorry. Andreas is good at embarrassing himself, so that's what we found out. So that's true. Brand new hire, Harvey Mudd. Awesome, that's true. I will update that soon. Okay, so the two main players for the talk that I want to introduce, polytopes for sure, and posets, right? These are two things that you saw in the title, and so we've had a really good introduction to polytopes over the week, so I'm just going to remind us that if you have a set of vectors, I can take the convex hull of those, and we can define a polytope that way. And then I could equivalently say, well, what if I just look at all the half spaces or hyperplanes that I take intersection of finitely many of those, and as long as they create this convex set, then I have a polytope. And two equivalent ways to describe this polytope. And if you need a good refresher of how that works, go to Appendix A, I think, in Matt's book. It's not short, but it's important. So yeah, so we have this nice description for our polytopes. And then for posets, right, just a quick reminder, we have partially ordered sets. We can represent them in Hasse diagrams where we're really just showing you the order in which these elements relate to one another. And so an edge between two elements tells me that, let's say, H below E means H is less than E in the poset. No edges between them tell me they're incomparable. And then there's lots of things you can say about posets. So given the definitions that we're going to see, a couple of those that I want to highlight is that you can take the join and the meet of pairs of elements, or really sets of elements. But when I'm looking at the greatest lower bound of an element, given two elements, what's their greatest lower bound? I'm going to call that a meet. So if I take C and F, what's the element that's above them? Sorry, I always get this mixed up. Our last speaker was some kind in talking about the dyslexia that happens in mathematics, and it's awful for me. So we take the thing that's below them, but the largest, that's going to be the element H. I can also look at the join, which is the least upper bound. So again, take C and F. I'm going to take an element that's greater than both of those, but the smallest such, that's A in this case, and then just another example of that. Okay, so we have meets and joins.
Question.
Yes, please.
How are you defining order here one more time?
Yeah, so order, I'm really just reading this from bottom to top. Yeah. And I do have like H is less than B in the partial order of the poset, but because there's this element in between, I'm only going to look at the ordering, sort of the minimal coverings.
Gotcha.
Yeah. Yeah, please, if I'm not looking, I apologize. That's such bad. I'm like teaching students right now back home about how to give good presentations, and I'm always like, look at the audience. And so please keep me honest. Okay, so we've got posets. Now, how do we sort of fit these two ideas together? So when we look at a poset, we can call it a finite distributive lattice if it has finitely many elements. For every pair of elements, a join and a meet exists, and they have to satisfy this distribution property here, right? The distributive lattice name makes sense. And so with this, we can then say, take such a finite distributive lattice, and let's define a mapping. And it's nice, we've seen lots of variations of valuation this week. So we have a valuation here on a poset as long as it satisfies this equality for elements in your lattice. Okay. So we have that now. So how do we turn that into a polytope? So I kind of just want to give you the evolution because there is a way to describe your polytope given these valuations. So we have Geissinger in the early 80s that said, let's take the convex hull of the set of valuations over a finite distributive lattice. Okay, so start with your finite distributive lattice. Consider these valuations. As long as they're between 0 and 1, I'm going to keep them. And then I'm going to take the convex hull. That describes a polytope. Not too long after that, Dobbertin said, well, the vertices of this are exactly those valuations that are 0, 1. Nice. And then later, or maybe in the same paper, I forget now. No, it's the same paper. We're using the fundamental theorem of distributive lattices, right, to basically say we don't need to worry about it being a distributive lattice. We can really describe these polytopes for any poset. And once we have that, then we get to the definition that we want to use, which I'm calling it user-friendly because it really says take a poset, look at the chains, write down what you see, and you have a polytope. Okay, so here's what that definition looks like, and we'll have an example to look at here. So we take our poset now, right? We don't have distributive lattices. It's just any poset that you are interested in. And the valuation polytopes has these points H that are vertices if and only if it comes from some chain in the poset. So that means I'm going to take my chain here, right? All these elements from the poset are in my chain. And I'm just going to create some ordering so that I can say if you're an element that's not in the chain, you get a 0 in that entry. And otherwise, you're going to get -1 to the position of the chain. Okay, so example to help us with that. Ugh, frustrating. I changed this last night because I've had an example that looks like this for so long that I don't like, and I forgot to change this. So this should say the chain A, B, F. Okay, sorry about that. Actually, and that's a good time too when I'm teaching and then the students are hesitantly like, didn't you mean that? And I'm like, oh, good job. I meant to put that there. You're paying attention. Okay, A, B, F. So that chain has the corresponding 0, 1, -1 coordinate point because A is in the first position of the chain, so it's going to get -1 to the 0. B is in the second, so it's going to get -1 to the 1. And then F is the last position, so it's going to get -1 to the 2. And then that gives me this point here. So we just consider all chains. They don't have to be saturated. And it's going to give me a collection of 0, 1, -1 points. Take the convex hull. That's your valuation polytope.
So it sounds a lot like, what do you call those matrices that are probabilities and the rows and columns all add up to 1?
Yeah, a Birkhoff.
Wait, the vertices of that are the permutation matrices.
That's true.
So is there a function that generalizes chains that is the fat interior to
I
this
have
polytope?
not thought about that. Great question. I should put that on the last slide. Yeah. Thank you. Does anyone else know? Great. If Matt says it's a good question. Okay, good. All right, great. So wait, now we have this nice vertex description for our valuation polytope. Okay, where did this problem come from? And I think we've heard it at least once this week. Solutions are born when you go to Stanley's, one of the Bibles, right? This one comes from chapter 4, question number 58. This is part of it here that we're looking at. And I think someone already pointed out that the numbering tells us, what's known. And if we have 5, and I guess it's a negative sign because he actually has a paper that kind of addresses some of these things, but really it's an open question. To just say, take your poset of interest, generate this valuation polytope, and ask some questions. Here he's sort of listing the basic questions you want to know. How many vertices does it have? What's its volume? Can you describe the Ehrhart polynomial? And then this last one is really like, now pick your poset, because he answers this question for posets that are a chain. And that's where we come in. Okay, so we're interested in taking posets of, height 2. And in particular, we decided, why don't we start with something that feels kind of chain-like, but sort of shrunk, right? And so we're like, we'll consider something called, we call the zig-zag poset. You might also see it called the fence poset in literature. But if I have 2 elements, right, it's the chain already. If I have 3 elements, I kind of just go like up, down, greater than, less than, as the inequalities in this poset. And so for each one of these, I can write down what their chains are. And I'm highlighting some things to kind of give us indication that there's some nice behavior here, right? Not only that, but any chain from the previous poset stays with the next poset, right? So we have some recursion perhaps. Each one of those chains turns into some 0, 1, -1 coordinate point. We take the convex hull of all those things, and here are some nice pictures to look at. Okay, so let me see if I can do this. This is always tricky. I just wanted to kind of highlight how these polytopes grow because it's going to show up later. So it is true, this is a 4-dimensional polytope. I will not draw that one. But I will say let's start with a 1-dimensional, which is something I left off of this slide. 1-dimensional is just the single element, right? So just for the sake of argument, zigzag 1 is just this element here. It has the chains 0, the chain is either empty or 1, which gives us 0 as one of my points and 1 as the other point. And so let's say this is x1 here, x2 and x3. So there's 0, here's 1, there's that polytope. Okay, to get to the next one, let me draw it here. So we have 1, we have 0. So the recursion is telling me that each one of these are now elements in the next polytope. So I'm just going to add a 0 there. And then the only things I don't have yet is this singleton here. So 0, 1. And then the chain 1, 2, which means I'm going to have positive 1, negative 1 here. And then this is kind of one of the key things and why I want to draw this is because we've got our odd dimensional polytope. To move to the even dimension, I am doing a bipyramid over the odd. Okay, and that's holds in general for this zigzag poset. So to go from odd to even, it's a bipyramid. And then to go from even to odd, all these chains persist. We've got 1, negative 1, 0. And then now what I'm missing is the singleton chain up here. And then the chain 3, 2, right? This chain here, 3, 2. And so that's going to give me a, let me make sure I do this right, 0, 1, negative 1. Sorry, I said that backwards. No, I said 0, negative 1, 1. That's how I get there for real. Okay, there we go. So then we take the convex hull. And like I said, to go from odd to even, it's a bipyramid. To go from even to odd, it's this tenting behavior. So we're always going to see that. Okay. And hopefully those look kind of similar. Okay, recursion is helping us. Oh, not yet. Sorry, punchline revealed. So, great. So now we have this valuation polytope. And I just wanted to say again, thank you to Ben, because I think there's very few times in your career when you feel validated, doing the right thing, asking good questions. And so when I saw Ben's slide, I was like, perfect, you wrote part of my talk, because these are exactly the kind of questions we were interested in. A few more than maybe we considered. But that's okay, right? Because that means we have more work to do. But so now we just say, well, what are the problems we're interested in for these valuation polytopes? Can we describe the facets or the vertices? Can we come up with some interesting volume formulas? Can we think about the H-star vectors? Or, we're thinking H-star polynomials, but now I know I can think about distributions maybe or other questions. Is there a nice interpretation for these coefficients? What else from here I can say? Well, if we have something known about those coefficients, maybe we can also say some other interesting things. Triangulations are helpful, and then a bunch of other stuff. Okay, but so I was very happy with most of this slide. I have good ideas. And so, yeah, just thank you for these small moments of validation. Okay, so let's get started on some of these questions. For most of the talk, I'm going to talk about how we think about volume for the valuation for the zigzag. We do know some of the F vectors, and we can tell you about edges and vertices and facets. Everything in between is still something we're thinking about, trying to figure that out. And then, of course, what can we say about Earhart theory? So that's all to come. All right. So here's kind of a big slide encapsulating the vertices, the edges, and the facets. So we actually have nice descriptions. If you have n elements in your poset, you're going to have exactly 2 n vertices, which is not too tricky. If you remember the color coding I did from the chains that we created, we're always adding just 2 new chains every time. And we started with 2 to begin with. This is a nice polynomial description for the number of edges, depending on the parity. And then same for the facets. So I can actually give you a nice way to think about the edges in terms of chains, which is coming. When it comes to facets, we did need to kind of revert back to the traditional way of understanding valuation polytopes to talk about this. So it does use this downset description from Geissinger. So I will say, talk to me later. Thanks for that. Okay, so what about these edges? Why do I have such nice polynomial descriptions for those? Well, it turns out that any height 2 poset now, so I'm not talking about zigzag, I just take any poset of height 2. These are the things, so these are the pairs of chains that do not form an edge in the polytope. I just drew the pictures because I used the pictures to help me figure this stuff out, and I like it, so I want to show it. If it's nice and you want to stare at that and understand it, great. Otherwise, just know that they exist. But it's really telling me among these collections of pairs of chains, I can ignore that stuff. Everything else, all other pairs of chains, give me an edge of my poset. So we have a nice way of determining what these edges look like. Now on to volume. Here's how we compute the volume. If you're odd number of elements in the poset, you're just a power of 3. If you have even number of elements in the poset, it's a power of 3 times 2. Pretty nice. How might one prove something like this? Well, it definitely helps if you have a unimodular triangulation, right? We talked or heard about this earlier in the week. That means I can subdivide my polytope into the simplices of volume 1, so that's really nice. So if I can do that, I just count how many simplices I have. Here's an example of what a triangulation could look like, right? Each one of these have volume 1, 1, 2, 3. There we go. So there's an example of that top value for k equal to 1. Okay, and again, it's like you want to share the nice things that you've done because you're proud of it, even if nobody else is really going to care. It's like bringing home the macaroni necklace to your parents, and they're like, sorry, Andreas, because he's part of I love macaroni, for sure. Here's our macaroni necklace, maybe. So the main point is we come up with a triangulation. We know that it's unimodular. I just count how many there are. I can give you what the vertices are. Because I know how to use that kind of recursive behavior, each one of these simplices gets split up by the new added chains, the new added vertices. And so then I know how to create a set of simplices that triangulate my polytope when I go from an odd dimensional one to the next step up, even dimensional. So I can tell you exactly what that triangulation looks like recursively. And then again, if I start with odd and I want to jump to the next odd dimension, it just splits it up into 3. So it's very nice. It's a nice recursive description, and I will maybe make a plug for discussion later. Recursion versus inherently, beautiful proof that is not recursive. Which one do you like better? Because we have a recursive, right? I know some people are like, yeah, you're using a crutch. So like, what's the nice behavior that might be really going on here? Describe it differently. I don't know. I just wanted to raise that point because it's been something we've been discussing. Is like, is this proof done, or do we need to come up with another approach? I feel good about it. Yeah. Okay, thanks. Yeah. Perfect. Okay, so now we have a nice way to use that recursion to give us triangulations. What else can we say? So just a quick reminder, right? We've got this nice polynomial that captures the integer count of lattice points and dilates of our polytope. You can throw that into a generating function, and you get this nice rational series, rational function, I mean. And what can we say about that top polynomial, right? What can we say about the integer count? And so that's really the rest of the talk will be about that, mostly H star. We are able to talk about the Ehrhart polynomial when we do this bipyramiding, right? So if I know the number of, if I know the Ehrhart polynomial for this odd dimensional polytope, I just bipyramid, and then I know what the Ehrhart polynomial is for that next even dimension. It's going from the even to the odd that's been tricky. So we're not totally sure yet how to do that, working on that. But then what about the H star polynomial, right? Can we talk about the coefficients somehow? We know they're positive, but is there some nice combinatorial description? Can we give a nice explicit formula? And it turns out that moving to a different polytope is helpful in this case. So let me just introduce the root polytope quickly, and then we'll be able to talk about H star. Okay, so quick intro to root polytopes. We're going to take the origin, and then we're going to take some graph, some acyclic oriented graph G. And for any edge in that graph, I'm going to include the indicator vector that's just EI minus EJ. So I less than J, that means it's an edge from I to J, right? Oriented in the graph that way. So I take the convex hull of all those, and I'm looking at a root polytope given that particular acyclic oriented graph. As an example, here is a acyclic oriented graph. The edge 1, 3 goes from 1 to 3. So that means I should see 1, 0, negative 1, 1, 0, negative 1 as a vertex for my polytope and all the other edges. And we take the convex hull and we get this. Good on that? Okay. So why am I introducing this? Well, for each one of our zigzag posets, think about taking it and just stretching it out flat, and you'll see those here. I'm going to orient it based on the poset inequality in that we see there. And then I'm just going to adjoin the sink to each one. So now we've taken every zigzag poset and turned it into an acyclic oriented graph, which means each one of these now has a root polytope associated to it. Okay, and just as another cell for why we might want to do this, well, there's the polytope that we already know from the valuation over the valuation polytope over Z2. Here's what I would get if I played the or acyclic oriented graph game with it. Here's the polytope, and hopefully you stare at these and go, ha, those must be the same, right? And luckily they are. All this says is integrally equivalent. Yes, they are. They are the same, morally the same polytope. So anything I can say about the root polytope that's really important, I'm talking about the valuation polytope. Let me just say it like that. So that means if I talk about the H star polynomial in particular for the root polytope, I have the H star polynomial for the valuation. So now this is the lens we're going to take to think about the valuation polytope. Everyone okay up to that point? All right. Hopefully this feels like that talk where you're like, hey, I understand something. I don't mind. Okay, so why is the H star polynomial the thing we're going to go after today? Well, thanks to Stanley, if you've got a unimodular triangulation, you actually have a really nice way to talk about those coefficients. So unimodular triangulations tell me that the H star polynomial is actually equivalent to the H polynomial over that triangulation. And what does that mean, really? That means if I look at the coefficients, so like H star sub I, that's actually counting the number of full dimensional simplices that have some nice property. I'm going to say it like that because you also need to have this thing called a Schelling order on the triangulation, which we've kind of talked about this week. But you can think of a Schelling as sort of a way to nicely induct over how you build the boundary of your polytope. And so as long as you have that order, count how many simplices share I many facets when you add it in the order, that's exactly what H star I is. That coefficient counts that information. So that means we need a Schelling. Okay, here's maybe where things get crazy, so let's see. We have graphs, which means we have spanning trees. And just for the folks, because we talked about matroids so much earlier, yes, we have oriented matroids too, but right, that's just on the side, okay, for now, just in case you're interested. But so we have spanning trees. What's amazing is every spanning tree corresponds to a simplex in our polytope. Only certain combinations actually represent triangulations, because we have to worry about intersections and all that stuff. But we're going to pick a particular triangulation that we're going to just quote unquote call it nice. And it's nice because it's the one I drew here. I mean, for other reasons too, but they all have the origin, and then we can kind of see this sort of nice like bouquet that gets sliced up. And so the spanning trees highlighted in green sort of represent that nice, those nice spanning trees that correspond to the nice simplices that we want. Oh, I said special, sorry, special. They're special to me. And so we're actually going to use that description to come up with this shelling. Okay, so first we have to make sure that we can always describe, we can determine among all the possible spanning trees which ones are part of that special triangulation. And they're always going to be of one of these three types. And the main takeaway from this is that I can break up my graph into subgraphs. And each time I look at a subgraph, I'm just going to ask, is it one of these three types? And in that index, so like in the first section, I'm going to index a 2 if I see these two edges here. I'm going to index a 1 if I just see this one right edge, and 0 if I see no edges. And that means when my graph grows, I first look at that first section, right? I have a 2, a 1, or a 0 to indicate the number of edges there. And then I just look at the next set of edges, and I ask again, does it have 2, 1, or 0? And that's how we end up with these indices. Okay. Yes, you can now look at the indices and sort of forget all that, but the reason is because the indices are really telling us which one of these spanning trees are adjacent, right? They differ by a single edge. But that is exactly saying that these simplices are adjacent. And that's what we want to know. Because if they're adjacent in the shelling, I can add it. Not only that, in the shelling, I can count how many faces now does it share with whatever I've added. Okay, great. So as an example, let's see. Oh, no, I think I did all this. Great. So let's see the shelling. And we had an idea of what we wanted. So we're using this as sort of our guiding light, right? Combinatorics 101, or even discrete math, or I don't know, nice video on YouTube. If I see this, K choose I should have K things, and I just want to pick I of them. And for each one of those things, I have two options, right? It's on or it's off. In our case, it's 0 or it's 1. And that pretty much told us how we needed to shell this so that that could work out. I know, right? Oh, who said that? Okay, well, appreciate that. Thank you. It is kind of a wow moment, I guess. Okay, this tells me what I'm doing. So if you want to read that and double check that the words I'm speaking match the words I've written, go for it. But let me just kind of give you an outline of what the shelling is saying. So if I choose no sets, I want one thing that I've added. Oh, wait, hold on, that's not adding. Let me just stop there, because all I want to know is how many things have I added that don't share a facet. That's just my first simplex. Okay, that's going to be the thing that has all 2s. So something that looks like this, right? It's an edge and then a bunch of edges kind of popping out. Now comes the next thing. I need to count how many how many simplices in my shelling, when I add it, share exactly one facet with whatever's present. Okay, and because I know that these indices are actually telling me by how much a spanning tree differs from another spanning tree, all I need to do is look at this index and say, if I'm 1 away, then I exactly have 1 edge different. And so, I kind of want to be like, well, I want to maybe do something like this and maybe do something like that. And then I know exactly how many simplices I've added that share exactly one facet. But this formula tells me do that in a nice way. Because first it says choose one of these entries, and then choose to turn it to a 1, and then to a 0. So choose the first entry, turn it to a 1, and then a 0. Now choose the second, turn it to a 1, and then a 0. Done. And we know they all differ by 1, and so these things share exactly one facet with what's been added already. Okay, next example, K, choose 2. Choose 2 positions, turn them both to 1. And now, among those 2, play the game again. Choose 1 position, turn it to 0. Choose the second position, turn it to 0. And since they differ by exactly 2 to the previous things, that's 2 faces. And then choose them both, turn it to 0, again, differ by 2, 2 faces. And there we go, that's the count. Did that make sense? Wow, okay, I wasn't sure. Sweet. Okay, and if you need it to be a little more complicated, here's just the next dimension up. But it's literally the same thing, right? It's just pick the all 2s, choose a position. Let's say the first position goes down, turn it to 1. The second position, turn it to 1, then 0. The third position, right? And Martina, I think, had this 4 by 4 by 4 structure. We are having a 3 by 3 by 3 structure, which is really cool. And we don't know if there's something connected there or not. I don't know. But yeah, so that's showing up here too. And this technically should be, sorry, triangulation of the root polytope here. So sorry for that typo. But so now we've got this nice Schelling order and a way to count. And that tells us exactly what the H-star polynomial looks like. Very nice. OK. That was only for odd dimension. I didn't really point that out when we were doing it, but this was only for when our zigzag poset had odd many elements. So what about even? Well, thank you to this theorem that says if you have a polytope that is really just a bipyramid over another polytope, which is why I kind of made this big deal of odd to even is just a bipyramid over the odd one, then we can describe its Ehrhart series. And so then we exactly have for even-sized zigzag posets, it's exactly our odd times this factor of 1 plus z. So now we also have a nice description for the H-star for that.
That would be the simplest polynomial that gives you the volumes you put up earlier.
Mm-hmm. Very true. And also, it's real rooted, which means it's unimodal. Very cool. So we get to check off a lot of things that Ben said were important. Most of these we've sort of addressed. I shouldn't say, check done, don't think about it anymore. But we thought about zigzag. I put up here that we have some preliminary results for other height 2 posets. One important thing to recognize here is that any height 2 poset is really like a bipartite poset, right? Which means I have m elements up top, n elements on the bottom, and then some relations. And so in some sense, we're kind of capturing that sort of section of a poset with this information, which is nice. So it's also good to kind of break it up maybe into certain cases as well, which is what we've been thinking about. Did you have a question?
Yeah. 2 slides ago, or you defined as a recursion, but then you say later that this only works for odd vertices zigzags. So I'm wondering, like here, what's like where does the odd vertex restriction come in?
Yeah. So if you look at the thing that we did to go from our zigzag to the acyclic oriented graph was take that zigzag that's like 1, 2, 3, stretch it out and add the sync.
Okay.
And here it's 5 add a sync.
Okay.
So we're actually jumping from odd to the next odd.
And you jump by 2, and that's why you need to cover a separate case. Yeah. Okay, that makes sense.
Yeah. Thanks for clarifying that. I apologize I didn't say that. Anything else? All right. Cool. What else are we thinking about? We've got, again, like I said, we have a recursive description of this triangulation. Maybe a non-recursive one exists. Can we describe the F vector in totality? That would be really awesome. Personally, I would love to be able to describe it in terms of the chains if we can. And then I haven't even touched this inequality description. Can we think of one? If you care about the root polytope exactly, we can think about all height 2 posets using that lens. And then, like I said, there are matroids hiding in here, so certainly there's a direction to take there if you're interested. So these are some things that we have on our plate to do. And then I tried to kind of cook up some ideas to foster discussion here. The easiest one is, what posets do you know that you might be interested in doing this, playing this game with? The only thing I can say about that is height 2 is like kind of naturally maybe the next step from a chain. And this problem has been sitting here for a really long time. Stanley didn't touch it since he, since he published that paper, blah. And so I think that means it's a hard problem. And matroid lattice of flats would be cool, but that seems crazy. There are these things called signed posets. That sounds cool, but maybe also kind of crazy. And then, I don't know, just like nice structures in lattice. Maybe there's some nice properties that pop up or some other kinds of ways of describing these polytopes with that in mind. So I really can't say how hard these problems are, but they seem really interesting and like really wide open. H-star polynomial, we can say some things about, but in particular, poset addition, you can describe using the H-star polynomial nicely. So what other operations or properties about posets might play nicely with this valuation polytope? And then because we often think about like maximizing or minimizing these values, I just threw it up here. Is there some nice poset structure that might maximize or minimize the F vector? I'm not really sure how tractable of a question that is, but it seemed like that's always a nice thing to ask. So I will just leave it at that. Thank you so much for your attention.